Global warming. This is part one of a projected 5-part lecture about the details of climate change on Earth, mostly in the last million years, but going back to 148 million years ago. So let us start with how ocean sediments were drilled back into layers up to 48 million years ago, because it had been never done before, and it was accomplished by using 3 icebreakers, and one of them's got the drill rig on it, and the other 2 fend off the ice flows so that the one with the drill rig can stay on station. And in that way, after they massaged all the data from the ocean sediments, they came up with the data displayed on this slide. PETM is the Paleocene Ecocene thermal maximum, which started out 48 million years ago and lasted 3 million years. BP is before the present. And during that time, the sea level rose to 66 feet, and that's the reference to that datum, because there wasn't any ice on either poles supported by land area, so the sea level rose to higher than it had ever been, I imagine. And the Arctic sea surface water, while it was 74 degrees Fahrenheit, it was fresh water at the surface for about a little over 500,000 years. And the evidence for that comes from the spores of the free-floating freshwater fern Azolla. And then, as you'll see in a minute, at that time, during the PTEM, the carbon dioxide in the atmosphere was around 1,600 parts per million, and hence the warm conditions in both poles of Earth. This slide just shows where long after the PETM, glaciers started to form in this region in Greenland. And these 4 sites there are where they took ocean sediment cores. And this is the oxygen 18 in the bottom sediments, varying from 0 to 50 million years ago. And there wasn't any ice in the northern hemisphere until the carbon dioxide got down to around 400 or 500 parts per million, and then decayed down to 200 parts per million. And then this is the bottom ocean temperature as deduced from the oxygen 18. Now this plot is of the from 29 to 39 million years ago, and these are just the name of that era, and these polarities means the polarity, the magnetic polarity of the ocean sediments, because they do have magnetic properties as shown in these two graphs, and because of the rotation internal to the liquid core of the earth that creates the magnetic field. Sometimes the north magnetic field isn't at the North Pole, but it switches around to the south. So this is just assisting in dating sediments. And these dots here are where the times that they sampled, at least, the drop stones, which are rocks and pebbles that were on the bottom of the glacier and was scoured by the supporting rock, and it made characteristic striations. And you can see there was little to no drop stones in the 250 micron or 125 micron region, and this is the rate of deposition in grams per square centimeter per 1,000 years. And it starts up about 37.7 million years ago. We're suddenly starting to see the large drop stones and also the 125 micron ones. And the 63 must have been wind-blown stuff because it was high even at 38 million years ago, but then decayed off and then buried around in step with the other one. So now we got time for one more slide here, and this will be the end of part one. The Kyoto Protocol is meant to reduce the heat trapping gases to 5.2 less than what was emitted in 1990. And the heat trapping gases are the ones they're worried about: carbon dioxide, methane, nitrous oxide. Sulfur hexafluoride is man-made, and these are the freons that are also man-made. They're leaving out the most important one, which is water vapor. And in 1991, there was 6,115 teragrams of heat-trapping gases. And 5.2% less than that would be 5,797 teragrams. And I might add at this point that the ICPP, the Intergovernmental Body for Climate Change, their only way to correct for the rising CO2 is to stop burning fossil fuels. And we'll see in later parts of this lecture that there's other options. But just to show how big this cut would be, in 2006, the total of all these gases was 7,000 some odd teragrams. And we'd have to cut that by this much, which is 18%. And to show you how big that is, carbon dioxide in 2006 was a total of 5,985, and home heating was 1,214. And even if we didn't allow anybody to heat their homes, it wouldn't reduce the production of carbon dioxide enough to meet the Kyoto Protocol, which fortunately we didn't agree to. And we'd still be 60 teragrams short of the Kyoto target. And the ICPP figured that the value of, or the cost to society of higher than allowed carbon dioxide is $43 a ton, which would mean, a teragram is a million tons. So for each teragram over the agreed limit, it would be costing society 43 million for each teragram, and so 60 times that would be quite a lot of money. And the last thing I want to mention, this old slide puts the population of the world at 6 billion, but as you remember, just in the beginning of 2012, the population exceeded 7 billion. And normal resting metabolism, a human will release a half a ton of carbon dioxide per year. And so 6 billion people, resting metabolism would end up with 1,220 teragrams. But for doing a lot of work, humans can emit 6 times as much. So just from humans breathing, we can almost get up to what the total of those gases was in 1990. So this is the end of part 1, and we'll just stop here for an instant.